Hello everyone and welcome back. So, what do we have here? We've got gears. You're like, no, I thought I escaped gears. You didn't escape gears. Gears are pretty much how we use angular acceleration all the time. And this time, sadly, that acceleration, not constant. Look right here, not constant. Which means probably some integrals. Just going to say it now. So, we know angular acceleration is 4t cubed, radians per second squared. And we know that the initial angular velocity is 20 radians per second. And that's for this gear right here. This big gear, little gear. And from that, what do we want to find? Well, we want to find the angular velocity. Okay, not too bad. An angular displacement, that's theta, of gear B when the time is equal to 2 seconds. So here's your plan. First off, kinematic equations, okay? For a variable angular acceleration, not the constant ones. You're going to have to use the ones that have integrals and derivatives in them. And then you're going to find a relationship between the angular motion to figure out where it is at 2 seconds. And note, this is for gear B, not gear A. This is for the big one. So once you figure out equations for angular acceleration, velocity, and displacement, you'll have to figure out equations how that connects to my gear B here. Now, with that in mind, you've heard enough. So I want you to go off, try this on your own, and see how it goes. Hopefully it goes well. So 3, 2, 1, and you're back. And you rocked it. You're like, I knew how to do this already. I took your solid mechanics class. Or I knew how to do this already because this is my second time watching the video. Either way, I'm happy you knew how to do it. If you didn't know how, keep on watching. Let's look at it together. So first off, the motion of gear A. That's the small one. We're going to use our kinematic equations. So right here, we're realizing that angular acceleration and our angular velocity are connected. And remember, that's coming from angular acceleration is equal to the derivative of my angular velocity. Okay? And then I just multiply on both sides to solve for it. So I take this integral from my initial angular velocity to my final angular velocity. Remember, it doesn't start at 0, it starts at 20. I do the same over here, and what I get then is that my angular velocity minus 20 is going to be equal to t to the fourth. Or my angular velocity is equal simply to my time to the fourth power plus 20. Then I can do a very similar equation for my angular displacement. That's theta right here. Angular displacement. I take my equation and I integrate again. Being very careful that I use the proper bounds. It's very simple in this one because it's just from 0 to t. And so I get my angular displacement is 1/5 t to the fifth plus 20t. So when t is equal to 2 seconds, your angular velocity is equal to 36 radians per second, and your angular displacement is 46.4 radians. But it didn't ask for this, did it? It asked for it on gear B. So how do they connect? Well, remember that the tangential component of acceleration and the velocity, not angular velocity, just the regular velocity, point velocity, between those two gears where they mesh has to be constant. So if I'm looking at the velocity components right here, they have to be the same. And if I want to, I can realize, okay, well, if I want to figure out what the angular velocity of B is, I can just solve for that. That's what I do right here. I solve it in terms of the angular velocity of A, and what is this? Oh, it's the gear ratio. It's actually 1 over the gear ratio, but close enough. More or less the gear ratio. And guess what? It's the same exact thing for angular displacement. Angular displacement. If you're wondering why that is, you can work it out if you wish. Like, for example, this guy right here. Oh my, this is going to be... We'll do it. We're going to do it together, okay? I want to show it to you. So this guy right here is has a 3 times larger surface area than this one right here. So 2 pi RB is equal to 3 times 2 pi RA. Okay? So this one's much smaller. So if you think about this, when I have rotated a full circle of RA, how far has it gone? Well, it's gone a distance of 2 pi RA, which is simply 2 pi RB over 3. It's only gone a third of the distance, so it's only turned a third as much. So this one turns 360 degrees, this one turns 120. So that's kind of where this is coming from. And if you look at gears, I would strongly suggest that you just check them out and see how those connect. If you got any sort of gears, just look at them and see how they move. And I think it'll help you. Clocks are amazing for this. So I think that's it for this time. Yep, those are just the answers. So thank you for listening. I hope this helps you, and I'll see you all later. So have an absolutely wonderful day. Bye-bye.